a simple example. The given inputs are a and b, that is both are integers, and we want to find a plus b. For this, the output, of course, is an integer as well, so the data type is an int, and I've named the function add to num. You can name it whatever you want, provided it is not one of the already inbuilt functions, it should be fine. So in this, I have defined another variable int sum, and this is equal to a plus b. So this is the operation that we have. So after this, we have gotten the output. Now we just have to return the output, with which we can just use the return operation and return sum. So with this, this function is complete. And if I just go to VS Code, you can see that this is how it looks. This is the function that I showed you about. And then how we call it is just, I have defined a and b and then some other variable c to be equal to the output of this function call. So that is add to num of a comma b. So with that, we can just output C. Let me just run it just so you can see. With that, if I run, the output is 3. That is 1 plus 2 is 3. So this works. Now let's take another example. Let's say we want to find the sum of the first n integers with functions. So let's write this actually. So let's define some n is equal to 4 and we want to find the sum of the first n numbers. How do we do this? Let's define some integer, let's say sum, and start with 0. And let's run a loop for n times and then add the numbers. So for int I is equal to 1, starting with 1, and then I less than or equal to n, end at n, and then I plus plus. So this is the for loop that we are making, and in each iteration we are doing sum plus equal to I, that is the number we are adding. So with this we have added 1 to n. So at the end of this loop, the output should be the value of the sum that we get, with which we can just return sum. So this is how we write the function over here. And then again, the call is just simple. Int sum is equal to the function call with n. So if I just run this again, it gives 10. That is 1 plus 2 plus 3 plus 4, because n is equal to 4 over here is 10. So this works. So we have seen the examples of two functions. Now, a function can call several other functions. So far, we have seen only functions that just gives this just does operations and gives output. But for these operations, we have not used any other function. We can also use other functions to do these operations. So for as an example, let's try to combine the sum and the add to num functions that we have seen so far. So here in this case, we are adding a number to sum, you see. So let's say we are not doing that when we want to use this function, add to num function. So let's just copy that and paste it over here so that we can use this. And what we are doing is in every operation, we are adding sum with I. So what we can instead do is change sum is equal to, we can call the function add to num, and then the numbers we are adding in this case is sum and I. So with this, we can use this add to num function to add instead of just using the operator. That is, we can call other functions if we need be. So running this, the output is still 10 and it works. So you can call any number of functions and any function can have anything else. So with that, that is just convenience. There are also a few inbuilt functions that we can use to our advantage instead of deriving them every time. So I've just stated a few of them over here. So pow function gives a power x, that is a raised to the power x. And then sqrt gives square root of the number that it is given as an input. And then max and min functions, this is pretty straightforward. You give two integers or two values of the same data type and it will give the maximum value of that and the minimum value of that. These are quite helpful instead of adding an if and else loop everywhere. We can just use max and min. And again, sort. I believe sorting has already been a session in ADaPT, so you will know this by now. Sort is another inbuilt function that we are using to sort a given array or a vector. And then swap, this is a little less known inbuilt function. This is used to swap the values of a and b. Suppose in the beginning we have a is equal to 1 and b is equal to 2, and we run the command swap a comma b. In this case, it swaps the values. So after this operation, a is equal to 2 and b is equal to 1 is the situation. So, and then the next is to upper. This is a function on characters, in which case we give it small letters, that is Latin letters are small, that is small a, small b, small c, and so on. And after this, after running the function, it gives the same letter but in capital. So it is capital A if you give the input a small a. So these are a few predefined functions. There are several of them. I just wanted to mention a few. So moving on from this, int main is itself a function. You see, let's look at int main. It has a data type for output and it has a bracket and a few others. We can give some inputs. What those inputs do, we don't see them in this session. So we can give as input and it returns a value as well. So int main is itself a function. And the thing is, the program, the software has predefined this function to be the first function to be called. So when you run a code in C++, it first calls the main function. And then any function that we have written over here are called inside the main function. And after the execution of the main function, the code finishes executing. So this is the first function call that the program makes. And this return zero is quite important. This return zero is not important to us. It is for the software to determine if the program has finished executing successfully or not. So if the return value is zero, then it means that the program has run successfully. So if it is not zero and something else, that means that the program has not executed completely or it has not run very well. So if you don't put this, let's say the program stops running over here and does not execute this part of the code, in which case it returns a random value from minus 10 power 18 to plus 10 power 18, in which case there's a very, very small chance that it is zero. So most of the cases it is not zero. So if it gets any other value, then it is not that which is not zero, then it means that the program has not run very successfully and there are a few errors. So that is just something that a few servers use, including code forces and such, which is not useful to us, but it is useful for the software. I just wanted to mention that. Now we move on to recursions, the important topic. Functions are a small topic and recursions are a part of functions. Recursion is a special type of functions which calls itself. You see, if a function calls itself, let's say we first call a function that calls itself again, which ends up calling itself because in the function it has a call for itself. So it keeps calling itself again and keeps calling until a base condition is satisfied. What this is, we will look at it. This is how recursion would typically look like. Function with an input and then base condition. The base condition is what is used to terminate the recursion because it keeps calling again and again. After the base condition, we have a few operations and then we call the function itself, the function itself. So this ends up calling another one of itself and it keeps going on until the base condition is satisfied. We will look at a few examples of recursions now. Let's say we want to print numbers from 1 to n using a recursion. We can use a loop for this, but let's try to solve this example using recursions just so we can understand how recursions work. Now, let's say I call one function to print the value of 1, and let's say that function calls another function to print the value of 2, and that function calls another function to print the value of 3. So that is how this recursion works. You see, I start with the call println of 1 comma n, that is, in this case, if I is greater than n, return this part is the base condition of this recursion. That is, this function is used to print numbers, right? And we want to print only from 1 to n. So if any number is greater than n, we don't want that to be printed because we don't want the last number to be n. So if the number is greater than, we are returning, which means we are stopping the recursion at that point. And if it is not, then it is going to print that number and call the function for the next integer, that is I plus 1. So this is the example on how we can print 1 to n using recursion. This is the function. I've just taken that from the slides. And for n is equal to 5, let's say, let's run this. And running this, we get, let me expand this a little bit, 1, 2, 3, 4, 5. So we have printed 1 to 5 using recursions instead of a loop. Again, you can do this using a loop, but recursions we want to learn. So we had used this example. Now, for understanding a recursion, how a recursion is, we use this concept called a recursion tree to visualize a recursion. So this uses the function calls that we have, all the function calls that we have used. In this function, in this code, we have called the functions println1 command, that is the first function that we called, which calls println2 command recursively, and it recursively calls println3 command, and it goes on so on till println command, which finally ends up calling println plus 1 comma n. And in this case, it satisfies the base condition because n plus 1 is greater than n. So how we denote a recursion tree is using arrows, we show the direction. That is println1 command is calling println2 command. So there's an arrow over here. This calls println3 command. So there's an arrow, and so on. We have more arrows. This part is the operations. This is not part of the recursion tree, but I'm just putting it over here so that we can better understand this. So first we call println1 command, which does this operation, that is prints 1 and then calls println2 command, which prints 2 and then calls println3 command, which prints 3 and calls println4 command, and so on. It keeps going on till println command is called, after which it prints n and calls println plus 1 command. This satisfies the base condition, and after this is satisfied, it does not print n plus 1, it ends up returning. Well, you can't really see that over here because of this, but it returns the value. So this is where the recursion stops. And this is how the recursion tree is for this example. And this is quite helpful for more complex examples of recursion. So moving on, backtracking. So now suppose for now we have seen how a recursion looks like is we have the base condition first, and then we have a few operations, and after that the last thing that occurs in the function is when we call the function itself. That is, the recursive call is the last thing that happens in the function. What if it's not the last thing? What if there are a few operations after the recursive call? That is, we have just interchanged these two lines. We have a base condition, obviously, and then after that we have the recursive call first, and then after that we have the operation, that is print the value of I. What happens here? Does it do the same operation, that is print 1 to n, or does something else? Because when this calls this function, it is within this, and this thing is still running when the recursion is going on. So this part is not executed. Let's quickly see what happens in that. So I have the same code, but I have interchanged these two lines, and for n is equal to 5, I have this function. So let's just quickly run this. Oh, sorry. So if you run this, it prints 5, 4, 3, 2, 1 instead. Now it prints the opposite order of what we had gotten initially. Why does it do this? Let's try to visualize this using the recursion tree instead, because it is more easier. So this is the recursion tree. Again, the same functions are called, but the operations is where this differs. So we have called println1 command initially from the main function, which does not go to cout1endl because it is after the recursive call. So it then goes to println2 comma n instead of doing the operation, which again does not print 2 because the println3 command call is before this. So it keeps going till the recursion. It does none of the operations. So it keeps going until it reaches println plus 1 command, in which case the base condition is satisfied. As we have seen, the base condition is always the first part of the recursion. So the base condition is satisfied for this regardless. So it returns the value. So after it has returned, if we look at the function println command, this had called println plus 1 command. So after this is done executing, then it will go to the operation that is after the call. That is, after println plus 1 command is done executing, it then prints cout/endl. So after n plus 1 command is done executing is when it does the operation. So after it does this operation, that is prints n value, is when println command is finished executing, in which case we can look at the function println-1 command, in which case after println command is done executing, it then goes to the operations and prints n-1. So that is how we go in the reverse order. That is, it keeps doing this until it goes till println2 command, and after printing 2, this is done executing, and println1 command, as println2 command is done executing, it then goes to the operation that is cout1. So with this, println of 1 comma n is also done executing, and that is the end of the recursion. So that is why we have printed n to 1 instead of 1 to n. So this is the use of a recursion tree. Now, how else are we supposed to print 1 to n in this same method, that is backtracking, instead of printing n to 1 that we have gotten before? We can obviously say that when we tried to print 1 to n, it printed n to 1. So if we want 1 to n, we should try to print n to 1. That is the reverse order. So in this case, this would be the function. That is, we are trying to print from n to 1, but operations are after the recursive call. That is, we start from n, that is starting with the call println of n comma n, that is the first number, which the base condition is that it should be greater than 0. So the last number should be 1. So after the base condition is not satisfied, it goes and calls println of n minus 1 comma n, which goes and calls n minus 2 comma n, and so on. It keeps on going as we have seen before. And then finally, in the backtracking, it prints the values from 1 to n. So this is how we do it. And this is how the code is. We have seen this already. I'm not going to run it. It is pretty straightforward. So here are a few examples that we can do with this same example, that is using the recursion that we have learned so far. So suppose we want to print the first n odd numbers, in which case, instead of just printing I, we are printing 2i minus 1. The same code, but we are printing 2i minus 1. That is the only difference that we have. And as for the powers of 2, instead of printing I, we are just printing 2 power I. That is using this predefined function that I have talked about earlier, that is power 2 comma I. So this is how we do these two examples. It is pretty straightforward. We'll look at more examples later. But before that, this is the QR for the attendance for this session. So I will wait for about 2 minutes or so. Make sure to go and fill this as soon as possible. We will be closing this form after 5 minutes or so. So fill this right now. I will wait for about 1 more minute. So fill it fast. Okay, I'm assuming everyone filled the attendance now. And if not, there'll be another time where the attendance QR will be shown, so you can fill it that time. Let me move on with the next topic. So for now, we have seen only void functions. That is, the recursion only does not give an output. It only prints a value. So we have seen only void functions. What if we want the function to return an output, that is give one output, all the functions including? How would that go? Let's solve one problem that we can see over here. Again, the same example that we used earlier for functions. Let's try to find the sum of first n natural numbers using recursions. So with the same logic that we had earlier, we have just replaced the operations with return. That is, again, the base condition is that we go only till n and we don't go after n. That is, if the number is greater than n, return 0. That is, the contribution by that number is 0. Otherwise, we return the number plus the recursive call for the next number. So the return I plus sum in of I plus 1 comma n is how we recurse this. So this would return I plus 1 if it is less than n, or it returns 0 if it is not. So it prints 1, it returns 1 plus 2, which calls sum n of 3 comma n, which prints 3 and calls, which returns 3 and calls sum n of 4 command, which returns 4 and calls sum n of 5 command, and so on. It keeps recursing like that. So instead of printing, we are just doing this all in the same return. So it ends up giving one output. Again, we start with sum n of 1 comma n because we are starting with 1. But before that, there is another method, because the last time we had to print 1 to n, we needed the order. We had to print 1 first, then 2, then 3, and so on. But when we are finding the sum of 1 to n, we don't need the order. We just need to add all of the values. So we can go in the reverse direction. So we don't need to have this as an input int n. So we can go from n, then n minus 1, then n minus 2, and so on till it reaches 1. And after which, if it is less than 1, it returns 0. That is, it stops the recursion at that point, which is the base condition. And other cases, it returns I plus sum n of I minus 1. That is the number plus the previous number's call. So this is how the recursion will be. Again, so this is how this is. I have written both functions, one of them as sum n 1 and sum n 2. This is where we use two inputs, that is go directly from 1 to n, and this is where we go from n to 1. And I'm calculating for n is equal to 5, and we are calling both of these. That is, sum 1 is sum n 1 of 1 command, the first function, and sum 2 is sum n 2 of n. There is only one input and the second function, and I'm printing both the values to make sure that both give the same output. So if we print, it gives 15. That is 1 plus 2 plus 3 plus 4 plus 5 is 15. So the answer is correct, and both of the functions give the same output. So both of them can be used. Although this function is more often used because this is more simpler than the other one. Instead of maintaining two variables, we will use just one variable as input. So that is the more widely used one. So again, we start with sum n of n because we are starting from n and going till 1. So going with the recursion tree for this example, we have returns as the operation. Now I just written return, but these all return to give the same value. By the way, I've just written it so that it can give more information. Sum n of n returns n and then calls sum n of n minus 1, which returns n minus 1 and calls sum n of n minus 2, which returns n minus 2 and calls sum n of n minus 3, and so on. It keeps doing this until it gives sum n of 1, which returns 1, and then that calls sum n of 0, which is the base condition where it gives which is less than 1, so it returns 0 and stops the recursion. This is the recursive tree, and all of these sum up to give one output, that is sum from 1 to n. So let's see a little bit of theory about this. So how are these functions called? We see that in the backtracking, we had seen that when we call a function, the operations after it are not done. So how does this work? How are all of these functions called within themselves? Let's learn the concept of stacks for this. So as you heard of the word stacks, let's take the example of a stack of books. And each function is one of these books. So when we run a program, I've told you that the first function that the program runs is the int main. So the first book that we are inserting to the stack of books is int main. So there's only one book on the stack right now. And in this, let's say we are calling the first recursive function println of 1 comma n. So that is a function that is running currently. So we are adding that book as well to the stack. This recurses and calls println of 2 comma n. When it calls 2 comma n, println of 1 comma is not done executing. You see, println of 2 comma n is called within this function. So unless println of 2 comma n is done executing, println of 1 comma n is not done executing. So it is still on the stack. So after this, it calls println of 2 command, and that is inserted on top of this, which calls println of 3 command, which is stacked on top of this, and so on. It calls till println of n command, and lastly the last book of println of n plus 1 command. This satisfies the base condition. So after it reaches the base condition, this function is done executing. That is println of n plus 1 command is done executing. We can take that book off the stack. That is, we have reduced to one book. And after that, after println of n plus 1 command is done executing, println of n command is also done executing. So this book can also be taken off the stack. So we keep taking off stacks when the function keeps finishing executing. So all of these functions are done executing, and it comes to println of 1 command, and after println of 2 command is done executing, println of 1 command is also done executing. So we can just take this out, and the only function remaining is int main. And after the whole program is run, int main is also done executing, and the program closes, and we have removed int main as well. So we have cleared the stack again. Now each stack occupies memory. So the more you add to the stack, the more the memory it takes. So we have a condition over here called a stack overflow. That is, because we cannot store infinite number of memory in our computers, there is a limit for each program. So there's only a certain number of functions that you can put in a stack. So for this, suppose you don't have a base condition in a function. So it keeps going so infinitely it keeps calling other functions. So we're adding about infinite books to the stack, which exceeds its limit, and after which it has used up all of the memory that was allocated to this file, so it crashes the file program. This condition is called a stack overflow when we are overflowing the stack limit. So that is why we have a base condition, so that it does not exceed this, and it runs only till where we want it to. That's why we stop a recursion, and this works for all the functions. And I mentioned only this for recursion because recursion is where you can like go on so till infinity without having a base condition. So with this, that's why the base condition is very important. So now let's go on to another sub case where we have multiple calls of the function within itself. So far in all of our sumn or println or wherever it is, we have had only one call of the function within itself. So it went linearly. So if there are more calls within the function, it branches out. You see, one function gives two functions, and each of the two functions gives two more functions. So there it's four functions. So it keeps branching on. Let's see a nice example about this. I'm pretty sure everyone would have heard of this Fibonacci series. Everyone would have heard of this. So for this, let's define f of n as 1 for n is equal to 1 and 2, and then f of n minus 1 plus f of n minus 2 for the other n values, that is n greater than 2. So we can already see that this can be recursed. This is the condition for our recursion. So we can already see that this would be the code. So if we go to the file and try to write the recursion, the base condition, of course, we have seen is 1 for n is equal to 1 or 2. So as we are going down, that is n minus 1 and n minus 2, the n value is going on reducing. So at one point it comes being equal to 1 or 2. So at that point, we have to hard code it to be 1. So that is our base condition. Sorry. So the base condition is if n equal to 1 or n equal to 2. This is our base condition. We have to return 1. So this is our base condition. Else we are going to return, sorry, I've named this Fibonacci. So Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this is our recursive function that we have created. Now it is not necessary to add more things to this, but I would recommend adding one more thing. Suppose the n that we give as an input to this function is negative. Nobody would think of doing that. It's mostly not done. So what if you give, in the off chance that you do give it, then it keeps going lesser and lesser, and it does not come till 1 or 2. So it keeps on going until infinity. So I would recommend else if n is less than 1. So if any number less than 1 is given, it is not a valid choice. So we just return 0 over here. This just reduces the number of bugs that your code has and counts all of the possibilities that the input can be given. This is what I would recommend doing so that your code is more flexible. So going on with this, let's run this. In the int main, I've actually made a for loop to print the Fibonacci numbers from first to the eighth number. So if we run this, we should see the first 8 Fibonacci numbers. So it printed 1, 1, 2, 3, 5, 8, 13, 21, which are the first 8 Fibonacci numbers. So we have written the code properly. So this is how the multiple calls work. And let's look at the recursion tree for this. This is where recursion trees are more useful when it is not linear. So first we have called f of n. That is, we started with the call of Fibonacci of n. This, provided it does not go to the base condition, it calls Fibonacci of n minus 1 and Fibonacci of n minus 2. So both of these are called. So it calls two functions, and Fibonacci of n minus 1 goes ahead to call two more functions, Fibonacci of n minus 2 and Fibonacci of n minus 3. And Fibonacci of n minus 2, this one goes to call two more functions, Fibonacci of n minus 3 and Fibonacci of n minus 4. So it keeps on going, and the number of functions at any time is 2 power whatever the number it is. So it keeps on going. This is exponential increase of function. And finally, all of these end up to be resulting in f of 2 and f of 1. That is Fibonacci of 2, Fibonacci of 1, which are the base conditions. So that is how it terminates. So this is the recursion tree for this example. Moving on with this. So now we are seeing about the theory of how recursions are. So I will show you a few questions as an examples for how to solve them using recursions. We will go difficulty wise. So let's start with the easy version. I will give you an integer n, and you have to make a recursive function to find if it is a power of 3 or not. That is, suppose I give you n is equal to 729. That is 3 power 6. So it is a power of 3. So you should print yes. Suppose I give you something like 162. It is not an exact power of 3. So you should print no. So that is how you should make a function. How do you do this? So because of time constraints, I'm not going to type this. I'm going to show you the code of how it is and explain every part of this. So let's see, for a number to be a power of 3, it should be first divisible by 3. That is the first criteria. If it is not divisible by 3, then already it is not a power of 3. So if n is divisible by 3, that is n percentage 3 equal to 0, then we recurse to give it n by 3. So if 3 power n is a power of 3, then 3 power n minus 1 is also a power of 3, right? So we recurse on till we divide 3 every time. And if it is not divisible by 3, then it is not a power of 3. That is, something is left after we divide all the 3's. So we return false. That is, it is not a divisible, not a power of 3. And the base condition for this, of course, after dividing all the 3's, we end up to give 1. So if n is equal to 1, we return true. And 1 is already a power of 3, that is 3 power 0. So it is again a power of 3 itself. So after we divide all the 3's in the number, if it gives 1, only then it is a power of 3. Otherwise, it is not. That is give false. And in this, if power, we have a number, and I have run this loop for 5 times to give you an example of how this goes. So if power 3, that is the function name of this num, is equal to 1, because we are returning boolean, it returns true, true being equal to 1 and false being equal to 0. So if it is equal to 1, that is, if it is true, then it is a power of 3. So we print yes. If not, we print no. So let's just run this quickly. So let's give a few numbers. Let's start with 729 as I talked about. It is a power 3, so it should give yes, which it did. It gave output as yes. So let's give something else. Let's give 9. Again, it gave yes because it is a power of 3. If we give 162, then it says no because it is not an exact power of 3. Or 18, it says no. Or some other number which is already not divisible by 3. Let's say 5. Again, no, because it is not a power of 3. So that is how this question goes. So let's move on to the next question with medium difficulty. So let's say you have a travel total distance of n, and with each step that you place, you can either move a distance of 1 or 2 or 3 units. That is, each step can be varied with the distance, and you have to find how many different ways can you cross this distance with varying types of units in each step. That is, let's say you have to cross three distance, and you can have three steps each having one distance, or you can have one step with one distance and one step with two difference, or because steps are different, you can have the first step with two distance and the second step with one distance. So with this, that is a different way that you can go about the distance, or you can just have one step with three distance. So how do we do about this in recursion? So again, let's see that code. Now we are considering all three ways. Now let's start with a distance of dist. So after this, let's say our first step is of distance 1. So after this, we are trying to find the number of ways that we can cross a distance of dist minus 1. That is, our first step is one distance. If our first step is two distance, this ways of dist minus 2 will give the total number of ways in which you can cross a distance of dist minus 2. So the same thing for the first step being 3, you print the ways of dist minus 3. All of these are summed because we are trying to find the total number of ways. So the base condition here is if dist equal to 0, then the distance that you have to travel, that is yet to travel, is 0. So you have already reached your destination. So that is one way. So you have crossed your distance. So we return 1. Otherwise, if distance is less than 0, in this case, you have exceeded the distance and gone past it. So it is not a possible way. So we return 0. So with this, let's say for n is equal to 4, I have written a description of number of ways there are. So we can have 1, 1, 1, 1 or 1, 1, 2 or 1, 2, 1 or 2, 1, 1 or 1, 3 or 3, 1 or 2, 2. So 1, 2, 3, 4, 5, 6, 7. There are total 7 ways that I have written over here, in which case we can cover a distance of 4 with the given step sizes. So let's run this again. It gives 7, which is what we counted over here. So it gives the correct output, and this is how we go about this question. Now we go to a little bit of a harder question. It is not that hard, but just trying to understand how this is done is what is the hard part over here. I will try my best to explain how it is. So we are given an array of positive integers, specifically positive. So how many subsets of this array have the sum of elements in the subset being equal to k? The k is given, by the way. K is an input and the given array of positive integers is the input. We need to calculate the number of subsets that this array has, which give a sum of k, and we have to print the number of subsets. So for this, I have written the code again. So this is a little bit longer, and I will explain every part of this. So let's say we are starting with an empty subset, and what we can do with this subset is either add the first number or skip the first number, and then move on to the second number. That is, add the second number or skip the second number, and then move to the next number. Add the third number or skip the third number, with which each number has a possible two possibilities, either added to a subset or not added to a subset. With because of that, the number of subsets is 2 power n. So that is how many possibilities we have over here. So I will explain it in detail. We are storing this in vectors because it is easier, and we can modify the size as we are adding elements every time. So we are starting with this vector as the given array, that is 1, 2, 3, 4, 5, and we are using this as a vector to store the subset of elements at that point. So this is the dynamic vector that we are using for this recursion. And then we recurse for the given subset starting, and then the given array and the index of the element that we are currently considering, and then the k value which is given. In this case, I have taken k is equal to 5. So going to the recursion function, first we have to check if the given subset already has a sum of k. That is the base condition. So int sum is equal to 0 is something I have defined, and I have run a loop for I is equal to 0 to subset dot size minus 1. That is all the indices of the subset array, and I am adding the subset values to the sum at that point. Now if this sum is already equal to k, then as the elements are positive strictly, so we cannot get any value equal to k after adding any other element. It exceeds k. So this is where this subset stops. So we just return 1. That is one subset that we have gotten. Else, if sum is greater than k, that is we have already exceeded k, then there is no way we can get less than k because there are no negative numbers in our array. So in this case, we return 0, or if the element that we are considering exceeds the array size, that is, we have only arr.size number of elements, and the indices go from 0 to arr.size minus 1. So if it exceeds this, we have completely extinguished our given array of elements. So we have made operations on all of them. That is also a base condition. So this or this, both of them will give a return 0. Those are the base conditions. Now let's see how we can recurse this. Now let's make a new vector called subset underscore inc. That is, we include the given element at index ind that we have as input. So we include this in the subset. That is, we push this arr of ind to this subset vector, and we recurse both of these. That is, first we have when we have not included. If we have not included element, the vector will be equal to the subset itself. So the input will be subset itself, and then the array, and then we go to the next element, that is int plus 1, the next value of the array that we are considering, and then the key value is just given again. Or if we consider that element and add it to the subset, then the input will be subset inc, that is included, and then array, and then int plus 1 considering the next element, and k value again we are given, and then these both sum because both of these are to be considered as the total number of ways is what we need. So after running this several times, it runs for all the elements of the array, whether it is included or not included in the subset. It gives the total number of subsets. This might be a little hard to understand, so if you have any doubts related to this, you can text me on WhatsApp as to how this works, and I will be explaining it. I'm running out of time, so I should finish fast. So with this, let's give this example. 1, 2, 3, 4, 5 is the array that we have given, and k is equal to 5 is our input. Let's first on paper see how many ways there are that subset will have sum of k. That is, as this is a subset, the order does not matter. So 1, 4 and 4, 1 are the same subset. It is not different. It is not a different way. So 1, 4 is a subset which add to 5. 2, 3 is another subset which add to 5. And then 5 as an element on its own is a subset which adds to 5. So we have gotten 3 so far. So if I just run this, the output should be 3. And then it does give the output 3. So this is the code, and all of these codes that I've written so far, I will be sharing it in a GitHub repository and then putting it on the WhatsApp group, including the slides that I've used. With this, I will be ending my session. Here is the QR for the feedback form. I hope everyone goes and fills this feedback form. I will be waiting here for about 2 minutes so that you do. And then with this, I will be wrapping my session on functions and recursions. I will be posting an code forces contest about 5 easy questions on recursions so that you will get to know about recursions. It starts at about 10 p.m. today, and I will be sharing these slides, of course. If you have any sort of doubt about this session, whether the slides or the codes or anything that I said during the session, make sure to contact me in the WhatsApp. I am in the ADaPT WhatsApp group, so you can always contact me, and everyone is welcome to do so. I will explain everyone's doubt. So with that, I will be wrapping my session. The session is not over yet. My part is over. That is, the first part is over. Next, Parijat will be taking over the next topic. That is, um, so please don't leave the session and fill this feedback form. I'll wait here for about 2 minutes. I hope everyone has filled the feedback form. Thank you for attending my session. Parijat will now be taking over.
Hello everyone, am I audible? Can
Yeah, you're
someone please?
audible.
Okay, thank you. Right, so this is going to be the second part of today's session. I'm Parijat Mukherjee. I'm a coordinator in the programming club of IIT Madras. And the topics we'll be covering in this session is prefix sum arrays and frequency arrays. So the first part of our session, prefix sum arrays. Let me first start with a problem. If you're given an array of n integers, calculate the sum of all elements from index L to R. Both inclusive means that it's going to be L plus 1, dot, 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 R minus 1, R. Like both are included. So how would we solve this problem? It's very simple. Simply we'll iterate over the required indices and get the sum. We start with sum equal to 0. From I equal to L to R, we add the corresponding element of the array and then output the sum. Hopefully no one has any problems with this. What would be the time complexity of this approach? So since L, the range of L and R can at most be n, which is the length of the array, we might do at most n operations and therefore it's on. Now here's a slight variation on that problem. You're given an array of n integers and q queries of the form LR. And now for each of these queries, you have to separately calculate the sum of all indices from index L to R. Now, how would we do this? One way is obviously to do the same thing q times. For q is equal to 0 to q, exactly it's the same code, sum equal to 0, input LR, add array elements, and then output the sum. Now, what would be the time complexity of this? We have an outer loop involving q steps, and then inside we just saw that the complexity can be on. Therefore, the total complexity will be o n times q. This is not ideal. O n q can be a pretty bad complexity. So how would we improve this? And the answer to that is using prefix sum arrays. So let me first define what a prefix sum array is. Suppose we're given a sequence R of n numbers, then the prefix sum array is a array called pref, which has n plus 1 numbers, such that the ith indexed element is equal to the sum of the first I elements of R. So in mathematical form, it'll be pref I equal to R0 plus R1 plus dot 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 Ri minus 1 and pref 0 equal to 0. I hope there's no issues with the definition here. Now, how would a prefix sum array help us with our original problem? Can you think of a way to get the answer to some query in terms of this prefix sum array? So this would be the sum we're targeting. We can rewrite it in this format. We take the sum from 0 to R minus the sum from 0 to L minus 1. I think you can see how all these terms will cancel out and you just leave this. And in terms of the prefix sum array, that would be this expression, pref R plus 1 minus pref L. Now this entire operation and this entire process takes only one operation because we're just doing one subtraction and that's it. So it's a constant time operation that is time complexity will be O1. So to do this q times, the time complexity is O1 into q, that is OQ. Now, how would we construct a prefix sum array? This we know from the definition that I told you. And using this, we can construct a recurrence or a recursive relation. So the base case is pref 0 equal to 0. And then from then on, the I plus 1th element would be the ith element plus the value of Ri. I hope you can see this from this. This would be pref I plus 1 equal to R0 plus dot 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 ri, which is also equal to r0 plus dot 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 r minus 1 plus ri. That is exactly what we're doing here. So this would be the code for that. It's very simple. You start with pref 0 equal to 0, and then from I equal to 0 to n, pref I plus 1 equal to pref I plus ri. The time complexity of this is again O(n) because it's pretty obvious. We're doing a loop with n steps, so it's O(n). Now let us analyze the performance of the two methods. The total complexity is O(n) plus q because first we do an operation with n steps, that is to construct it, and then q steps to return answers to the queries. So total that would be n plus q, and that's a lot better than O(n)q because consider these values of n and q. The prefix sum array would be n plus q equal to 2 into 10 power 5. But the brute force method which we used before, that would be 10 power 10 operations. That's too much, and that would give you a time limit. So for the original problem, to return the answers to the queries, this is the code. Simply input L and R. It's assumed that we've already constructed the prefix sum before, and then use this formula to output the answers. The time complexity of this would be O(n) plus q, like we just saw. Now, here are some applications of prefix sum arrays. The first would be to efficiently find the sum of the elements in a subarray. This is what we just did. That's the whole idea behind it. So here's a problem for you. I want you to scan this QR code and vote in the Slido poll. Given a sequence A of n integers, for positions 1 less than equal to L, less than equal to R, less than equal to N, what is the value of the sum AL plus AL plus 1 plus dot 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 AR? Read the question very carefully because there is something in here that's different from what we've been doing. I'll give you a few minutes to attempt this. Right. So the correct answer here would be pref R minus pref L minus 1. So if any of you have voted otherwise, I think a lot of you might have voted for pref R plus 1 minus pref L. There's a reason that is wrong, and I'll explain it here. So when our indices start with 0, which is how I'd introduced this, this is the formula. This is the one I taught you. But when indices start from 1, everything gets shifted by 1. So R plus 1 becomes R and L becomes L minus 1. So the time complexity of this is O(n) as we've seen, but it's very important that you know the difference between these two cases because 0 indexing is usually how we handle things in code, but 1 indexing is usually how things are given in problems because code forces problems often use 1 indexing, and it makes sense because real world we start counting from 1 and not from 0. So the type of error that is caused when you use the incorrect formula here is called an off by 1 error. And that is pretty important to avoid because it can unnecessarily introduce mistakes into your answer. Now, a second application is finding the k element subarray with maximum sum. What this means is a subarray is a sequence of elements of the original array. So a k element subarray would be any continuous sequence of length k. And for all such sequences, we want to find the maximum sum. So the way we do it is we iterate over all the possible subarrays of size k, that is 0 to k minus 1, 1 to k, and so on until n minus k to n minus 1 to check which of them gives the maximum sum. The implementation is something like this. We have our sum variable, and for every such subarray, we calculated the sum using prefix sum. And then if that is greater than max sum, we update maxsum correspondingly, and finally we output it. The time complexity of this would be O(n) because again, we're iterating through this maximum n times. If k is 1, then at max you'll have n such subarrays, which is each of the elements themselves would be a subarray. So that is O(n) complexity. A few things to note here. Why are we starting with maxsum equal to pref k? You see, this is also connected to the second question. Why are we starting the loop from 1? The very first array, what would that be? 0 to k minus 1. So L is 0 and R is k minus 1. So our answer is the prefix sum method will give us pref k minus 1 plus 1 minus pref 0. So that is just pref k itself because pref 0 is 0. So it'll just be pref k. That would be the answer for the very first one. If we had started from I equal to 0, we'd also be including that. But since we've already computed it, we're starting from I equal to 1 and updating accordingly. There's a way to make this simpler actually. If we use this code instead, we start with maxsum equal to int min. This int min is a constant value that is the lowest. It's a very large negative value, the lowest value that can be stored in an integer type variable. So then what we do is we start from 0 only, not 1, and then maxsum equal to max of maxsum and our calculated new sum. This max function is also very useful. It max of a and comma b would return the higher value between a and b. So you can see how this makes life simpler. You don't have to worry about computing the first case separately. We just initialize it to int min because we know that no matter how bad the answer is, it's never going to be as small as int min because int min is the smallest value that you can have in an integer variable. So for the first case, this will automatically catch that because everything is going to be bigger than int min. Therefore, max will just take that new value and not int min. Right. The third application, this one's a little bit complicated, so try to pay attention. Finding the subarray of any non-zero length having maximum sum. So earlier we did for k elements, but this would be for 1, 2, 3, dot, 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 n elements. Out of all these cases, which one will have the maximum sum? So this one's a little trickier. You might think of one idea that for all values of k we iterate, but that will actually introduce two loops and will give you an n square complexity. So instead what we do is this. So what we want to maximize is pref r plus 1 minus pref l for some values of l and r. And since we want to avoid two loops, let us try to keep one of these somehow constant. Then it becomes an O(n) operation, right? Say if we manage to keep L constant, then all we have to do is check for all possible R. The way we do, like the logic behind this is for some specific R, when is this sum maximized? That is when pref L is minimized because there's a minus pref L in this term. So we want to incorporate the minimum value of pref L for any R. So this is the implementation behind that. Min pref is the variable storing the minimum value of pref L that we have encountered till now. And maxsum is obviously the maximum sum of a subarray. We initialize min pref to int max because we're going to be using the min function. It just works just like the max function. And anything is going to be smaller than int max. So that's what we initialize it. And maxsum, as I already explained, it's initialized to int min. Now min pref would be min pref and pref I. So pref I, the current I, that itself would be our L. So if we ignore the second line here, what this does is up till now it will give you the minimum value of pref L for some L encountered until now. With that, max sum equal to max sum pref I plus 1 minus min pref. This is the interesting part. Pref I plus 1 is what we're taking as pref R plus 1 here. And min pref is the minimum value of pref L. So for this R, this would be the maximum sum. And for all R, what it would be, that is what we're checking because we check it for every possible R and then update maximum accordingly. Finally, we output our maximum like usual. Again, this is an O(n) algorithm because Instead of two loops, we're only doing it in one. So that's n operations. Now here's an example problem. Yeah, this is a problem that took from Code Forces. Take a few minutes to read it and let me know in the chat if you get any ideas on how to solve this. Right. So let us take a look at this. What we're doing is we're given an array of n elements. We answer Q queries of the form LRK. And for each query, if all the elements AL to AR are changed to K, then will the sum of the entire array be odd? So you can take a look here. An example test case. Here, if we have 2, 2, 1, 3, 2, for the first query, the second and third elements are changed to 3. So that will be 2, 3, 3, 3, 2. The sum of which I believe is 13. 13 is odd, hence the answer is yes. Meanwhile, if we take a look at this 1, 4, 9, elements from 1 to 4 are changed to 9. So it'll become 9, 9, 9, 9, 2. The sum of that is 38, I think, which is even. So the answer is no. So I hope you understood the problem. Now let's take a look at how we're going to solve this. Can we compute the sum for each query, the new sum, the sum of the entire array that they're asking? Forget even or odd. Let's first compute this sum and then we'll worry about that. So the sum of the new array would be the sum of the old array minus the sum of the old subarray plus the sum of the new subarray. When I say subarray, I mean this thing, AL to AR. So what we're doing is we have the old array, we're removing all the elements from L to R, and then we're adding all the elements again in this, but this time they're all K. So the first term would be pre-computed. Sum of the entire array is easy to calculate as it won't change. The second term we can find using prefix sum. We know how to do that for values L and R. And the third term is K times the length. That is, since we're adding K elements length number of times, it's K times length added to the sum. Now let's take a look at the implementation of this. We start with inputting our N and Q. We have our array, we construct the prefix sum array, nothing new here. And now for every query in range Q, we input L, R, K. Now sum is prefix N. You could also write it as prefix N minus prefix 0, but since prefix 0 is 0, it's redundant. Prefix N is the sum of the old array minus pref R minus pref L minus 1. That is the sum of the old subarray under one indexing. That is pretty important to keep in mind. And then R minus L plus 1 times K. That is this term, K times length. Why this plus 1? If you take, say, L equal to 1 and R equal to 2, that is 1, 2, right? That is two elements. 2 minus 1 plus 1. That's why the plus 1 comes in. So now we've found a sum. If this sum is odd, if the remainder with 2 is 1, Then we output yes, otherwise no. Pretty simple. Now there are some extensions of prefix sum array that we use. Like the addition operation, we can also make a prefix array for other operations. We can have for multiplication where instead of subtracting, we now divide. We can have bitwise XOR where instead of subtracting, we now take the XOR. But don't worry too much about these. Mostly you'll only encounter the sum one, at least for easier problems. So this is a QR code for the attendance for this session. I'll give you a couple of minutes. Please scan it. If you miss it, that's fine. I'll show it at the end of the session also. Okay, since we're a little bit pressed for time, I think I'll move on. Don't worry, I'll show the QR at the end also. So now the next topic of this session, that is frequency arrays. Again, I'll introduce this by explaining why we'll need it, how we'll use it. So the problem we're considering is how do we count the number of occurrences of each element in a given sequence? This number of occurrences is called the frequency of that element. So if we know the range of values that elements can take, say if we know that all the elements are from 1 to 10, we can maintain a count for each value. Like we can count how many times 1 occurs, how many times 2 occurs, and so on till how many times 10 occurs. So we construct an array of all possible elements and then store the frequency of each element in the corresponding value. This is called a frequency array. There's nothing too complicated about this. So here's an example in case you, to help you understand. If this is a given sequence, it's a random numbers that I picked. What would be the frequency arrays? So the answer to that is this. The frequency array is this. I've kept the indices till 8 because that's the maximum value. So 0 occurs 0 times, 1 occurs 2 times, 2 occurs 2 times, 3 occurs 1 time, 4 occurs 1 time, 5 occurs 3 times, and so on. This is what the prefix, what the frequency array would look like. Now, what kind of steps did you use? Like, if you were to forget the computer, if you were to do this on pen and paper, how would you quickly do it? So, one way might be that you calculate first, you count, go through this 9 times. First, you count how many zeros are there, then how many ones are there, then how many twos are there, and so on. But that might take a little time. So, instead, a better approach is something like this. We start with everything 0 because we haven't counted anything yet. And then every time we encounter a new element, we increment that count. So for example, the first element is 1. So freq 1 is updated to increase by 1. Second element is 5. So that is updated. Then same for 6, 3, 2, 1, 4, 5, 2, 6, 8, 8, 5. So the way to do this in a code format is we initialize the frequency array with as many elements as we need. In this previous example, since numbers vary from 0 to 8, we need a 9, but that would be indicated by whatever limit is. Here limit was 8. In your problem, it might be something else. And then we iterate through the array, and for every element, increment the corresponding count by 1. Why am I using a vector here is because in arrays, the elements are initialized with some garbage values, but in a vector, they're initialized to 0 automatically, so that saves us some work. The time complexity of this construction would be O(n), because again, obviously, we're performing n operations total, therefore it's just O(n). Here are some ways we can use frequency arrays. The first is accessing the frequency of an element in some sequence. This is like that's the whole point of what we did. That's why we use frequency arrays at all. And the way to do that in code is to simply use the value at the corresponding index. F equal to freq x for the number x. That's it. The time complexity of this is O1. It's a single operation, so just O1, constant time. And the second class of applications would be anything that requires the frequency of an element. One important subtopic in this is counting problems. These are sometimes encountered on code forces. Counting problems involve permutation and combinations, which you probably know from JE and all, but I'll still give you an example. So if the problem is to count the number of pairs of equal elements in an array, what will we do? First, let us make the frequency array. Then for every number, if the frequency is x, then we add xc2, that is x choose 2 to our count, because we have x identical elements and we want to choose pairs out of them. So any pair out of these x can be chosen. That is why xc2. It's a fairly simple thing. Now here's an example problem for frequency arrays. Again, take a look and try to think of an approach. I'll give you a few minutes. Right. Hopefully you've gone through the problem once. I'll explain the problem and then as before, I'll explain the solution. So leaving this big story aside, what this is asking is we'll be given a string of length n, and then in that uh, we have to make sure that so every letter represents a task, right? If we begin some task, we cannot get distracted to another task and then return to it. What this means is if we have, say, in this string, we have B here, we're doing the task B, then later we move to C and then come back to B, that is not allowed. Uh, Similarly here, B and B occur with A in between, B and B occur with this whole block in between, A and A occur with Z in between, and so on. This one is allowed, FFG, ZZ, ZY, because uh, there is no, we're not returning to a task after doing another task. Now, the story aside, in terms of programming, what this is asking us is we have to check whether there is some letter that is occurring in multiple blocks with other letters between them. Like here, there are two blocks of A with something non-A between them. Here, there's two blocks of B with something non-B between them. That is what we have to check for. The test cases are exactly the same as given in the question. So these two are not allowed. because A and B are repeating, these three strings are allowed because there is no repetition like that. So the way we'll solve this problem is we need to keep track of letters that we have encountered before. That is what, right? So if we go through the string one by one, we come at B here, we should realize, oh, we had seen B before. Therefore, they should not be allowed. Similarly, here, if we go to the sixth element, we'll realize, oh, we have seen A before, so this is not allowed. So how can we keep track of letters? One way is using a frequency array for the letters. Since there's only 26 letters, it's pretty efficient. So for suspicious strings, that is when there is a problem, the current letter will have occurred before in some other block. That is, it is not the same as the previous letter and it has a non-zero frequency. It has a non-zero frequency as in it means that has occurred before this occurrence, but it should also not be the same as the previous letter because, for example, this string y, if we go to the second y, we'll see y has a non-zero frequency. It has occurred one time. But that does not mean it's a separate block because it's contiguous. The previous one was also y. So that's not a new block. And then the implementation of this problem. We input our string. We initialize a frequency array of 26 elements. We have a string for our answer. We'll start off as yes, there's no suspicion. And then if there is some repeated block encountered detail, we change it to no. So we iterate through the string. If frequency of si minus a is greater than 0. Why am I doing this minus a here? Is because this is si would be a character, but our vector is indexed by integers. So if si is say b, then b minus a would be 1. I hope you know that in C++ characters can be subtracted to give the difference. So b minus a would be 1 and it will check freq 1, that is the second element, that is b itself. So if that frequency of the current character is greater than 0, then if this previous element, that is si minus 1, is not equal to si, we change our answer to no and break out of the loop. If we haven't break out of the loop yet, we'll update our frequency for this current letter also. That is freq of si minus a plus plus. And then finally we'll output our answer, because if it hasn't been changed to no ever, then it'll be yes. Otherwise, there is some problem and it'll be no. Now, something to keep in mind here. What if I equal to 0? If you look at this line of code, how does this handle the case where I is 0? Because if you directly access si minus 1 and I happens to be 0, then the language will be like, what is the minus 1th element? I don't know. It will throw some kind of error, maybe a segmentation fault or something. So the way this handles that is I minus 1 greater than equal to 0 would be evaluated to false, because 0 minus 1 is minus 1, which is not greater than or equal to 0. So this is false and something. If you know about Boolean algebra from school, you might get a hint from this. False and something is always false, because false and true is false, false and false is also false. So no matter what this is, if we have decided that the first one is false, the entire thing is going to be false. So the language knows this, and what it does is, if it ever encounters something like this in a conditional statement where we're evaluating something and something, and the first thing becomes false, it does not even bother to check the next part. It straight up says, okay, this is false, okay, move on. Therefore, when I equal to 0, this will evaluate to false. This will be completely ignored. It'll move, okay, I'm not entering this loop. We'll continue after that. So that is how this error is handled. There is also something similar to a frequency array that you should be aware of. In this previous problem, if you noticed, we don't need to keep track of how many times some letter has occurred. We only care whether it has occurred or not. If it's occurring 1 time, 2 times, 10 times, 100 times, it's not important to us. So instead of an integer array, we can use a Boolean array. The implementation would be like this. It's exactly the same. From vector int, it becomes vector bool. And then here, instead of checking whether the count is positive, We just check the Boolean value. If found, if it is true, it'll enter the loop, otherwise it will not. And then at the end, we update found to be true. Like found of this character equal to true. That indicates for future operations that this character has been found and has been visited before. And then input the output the answer. Everything else is exactly the same. So one last thing, the frequency array idea has some limitations. You see, the size of the array is equal to the range of the values of the given elements. Like I said, when we have 1 to 10, then we need 10 elements in the array. If we have 1 to 10 power 9, we need 10 power 9 elements in the array, even if the input itself is only 10 power 5 numbers. So in this case, it's not efficient to create such a large array for so few numbers. And for cases like this, we use a data structure called maps, which you'll learn about in a later session. Don't worry about that for now. So that's going to be all for this session. Please scan the QR codes for feedback and attendance. They're both important in case you missed the attendance before, and your feedback is very important to us. It helps us to improve our sessions. So take a few minutes and scan this. And meanwhile, does anyone have any doubts? Please put your doubts in the chat. I'll try to address them. Okay, if no one has any doubts, then I'll conclude the session here. Thank you for attending, everyone. And please do attend the code craft session too. Thank you.